Hello everyone, welcome to Exploring Technologies. In this video, I will explain about the evolution of the Laplace and the Z-transform from the Fourier transform. I will discuss the problem of the Fourier transform. I will show you that for what types of signals the Fourier transform fails and how this problem is dealt by the Laplace and the Z-transform. So let me show you the contents of this video which I will cover. First, we will review the Fourier transform. I will show you the formula of CTFT and DTFT. Then I will discuss the problem of the Fourier transform, and then we will see that how this problem is dealt by this Laplace transform. So we will see the birth of Laplace, and for discrete time signals, similarly we will see that how the Z transform deal the problem of the Fourier transform. So let's go ahead. The Fourier transform, as we know, it can transform both continuous time signals and the discrete time signals from time domain to the frequency domain. So for continuous time signals, let's say xt, the Fourier transform is given by this relation. So x omega is the frequency domain representation of the time domain signal xt. So it's a complex transform. So with this formula, you can find this Fourier transform. This relation is known as the CTFT, continuous time Fourier transform. And the inverse Fourier transform can transform the frequency domain representation back into the time domain, as you can see here. And that is the relation. With help of that, you can transform your frequency domain representation x omega into your time domain signal. And for discrete time signals, let's say xn, the Fourier transform is given by this equation. So x omega equal to sigma n equal to minus infinity to plus infinity xn e power minus jn omega. This is known as the DTFT, discrete time Fourier transform. And the inverse exists, and it is obtained by this relation. So you can get your signal back xn from xj omega with this equation. Okay. So now let me show you what is the problem with the Fourier. So if we see both equations of CTFT and DTFT, we can see that here the integration is from minus infinity to plus infinity, and the summation here is from minus infinity to plus infinity. So Fourier transform fails when the signal either xt or xn, they are of constant magnitude with respect to time, or they are increasing function of the time. For example, if xt or xn are, let's say, having some constant function, or they are increasing function, then obviously this integration and this summation will give you the infinite value. So they will not converge. So that is a problem with the Fourier transform. So for such signals, the Fourier transform fails. So here we can see a few continuous time signals for which the Fourier transform fails. So this is your increasing magnitude is continuously increasing function. You can see. So with time, as t is approaching infinity, the magnitude is increasing here, here, and here. And here you can see the magnitude is constant with respect to time. So when you do the integration, obviously you will get the infinite values. And here are some discrete signals for which Fourier transform fails, Fourier transform formula fails. So this is the increasing, this is exponentially increasing, exponentially increasing. This is a sinusoidal and exponentially increasing, and this is the constant function. This is also exponentially increasing function with the time. So for such signals, Fourier transform formula fails, and you cannot find the proper expression of the Fourier transform. Although for certain signals like this, where the magnitude is constant, so by applying some tricks, we find the Fourier transform, but that is not directly from the Fourier transform formula. Okay. So now question is that how to deal this problem. So let's see. So to solve this problem of unbound integral, we can multiply the signal xt with an exponential, let's say e power minus sigma t before taking the Fourier transform. So now xt, instead of taking xt, let me take xt into e power minus sigma t. So where sigma is a positive number, so as sigma is positive, therefore e power minus sigma t is definitely decreasing function with the time as t approaches infinity. So this we can see in this figure, that e power minus sigma t is decreasing exponentially with the time. So because of this decreasing function, which we have multiplied with the xt, as e power minus sigma t is decreasing, so definitely the product xt into e power minus sigma t will decrease with the time, whether xt is constant or it is increasing with the time. Okay, so that will solve the problem. So in this case, if I take Fourier transform of xt into e power minus sigma t, the Fourier integral will converge for all types of xt. So now I will take Fourier transform of xt into e power minus sigma t. So I have used that formula, integration. Instead of xt, I am keeping this product, and then this is a complex exponential. So combining these two exponential, I can combine these two e power, so I get this expression. And then let's say assuming s equal to sigma plus j omega, so I can replace this sigma plus j omega with s. So I get this expression, and you know what it says? This is the expression of the Laplace transform. Okay, so therefore I can say that the Laplace transform is a generalized form of Fourier transform. So as it is showing that all types of xt now can be converted into the xs, whether xt is constant or increasing with the time, since I have multiplied that with the e power minus sigma t. So it means the integral will definitely converge for all types of xt. Okay, so this is the generalization of the Fourier transform, and we are getting Laplace transform for continuous time signals like this. So now let me show you the relation of Fourier and the Laplace on the S-plane. So actually taking Laplace transform of a time domain signal, let's say xt, is actually a mapping process with this formula. I mean formula of the Laplace. Okay, so all the points of xt are now mapped to the points in S-plane. So this is the S-plane. You can see this is your real axis, as sigma is a real number, and this is the imaginary axis. So this space is known as the S-plane. So if I take lots of points on the xt, those points are mapped to the S points in this S-plane. And the mapping relationship is this, that is the formula of Laplace. So now if I keep sigma equal to 0 in this equation, which is the Laplace equation, so when I put sigma equal to 0, this is the sigma. So sigma equal to 0, so this Laplace becomes equation of the Fourier. So Laplace becomes Fourier when sigma equal to 0. So where is sigma 0? Obviously sigma is 0 only on this vertical axis, I mean j omega axis. So I can say that out of all the points in the S-plane, only the points which are on the j omega axis, they contribute the Fourier transform. So I will say that all the points on j omega axis contribute Fourier transform points. So Laplace transform becomes Fourier transform on this vertical axis. Okay, so if you have a Laplace transform of some function, let's say e power minus at, so Laplace of this is s plus a. And if you want to find the Fourier transform of e power minus at, then what you need to do, you simply put s equal to j omega to get Fourier transform. So you simply substitute j omega in place of s. So that is a Fourier transform of e power minus at. But this you can do only for those types of signals which are decreasing with the time. I mean, for them Fourier transform exists. This you cannot do for the constant function and increasing function. Okay, so for them you have to find the Laplace transform. And now let's see the birth of Z-transform. So as we know, the Z-transform formula is given by this. So to make the summation sigma to be finite, when xn is multiplied with a sequence, let's say r power minus n, it is exponentially decreasing because r is positive. So r power minus n is a decreasing function with n, as you can see in this figure. So the path is same as what we have followed in the Laplace. So in Laplace we multiplied xt with e power minus sigma t. So where e power minus sigma t is exponentially decreasing. So xt is either constant or increasing with the time. The product will definitely decreasing. In the same way, we have xn here and we are multiplying xn with r power minus n. So r power minus n, as you can see, is exponentially decreasing with n when n approaching infinity. So the product xn into r power minus n will definitely converge. So this will solve the problem of Fourier in case of discrete signal. So now I will take Fourier transform of xn into r power minus n instead of xn only. So in this formula I have kept this xn into r power minus n instead of xn only. So now I am taking Fourier transform and now combining these two exponentials, just taking power out of these two. So I can write r e j omega power minus n, right? Now let me substitute, let's say z equal to r e j omega, and here z is a complex number. As you can see, this is r e j omega, it is a polar representation. Okay, so any point z is represented by the distance from the origin r and this angle j omega. Okay, so it is polar representation, so z is a polar number, while in Laplace we put s equal to sigma plus j omega. So any point in s plane is a Cartesian point. So this is s sigma and this is j omega. So that was the Cartesian representation, and here in Z transform, this Z is a polar representation. So when I substitute Z equal to R e j omega, I get this relationship. So this R e j omega is actually the Z. So that is Z power minus n. And what is it? This is the formula of the Z transform. So now I will say that the Z transform is again the generalization of the Fourier transform because xn, whether it is a constant function or it is increasing function with the time, by multiplying this r power minus n, definitely this product will decrease with the time. So the sigma will not become unbound. So now Z transform can deal all types of signals xn. Okay, so now let me show you that the relationship of Fourier and the Z transform on the Z plane. So again, xn is converted into xz. This is a mapping process, and the mapping is actually the Z transform formula. So this is the Z plane, and it is a polar plane, as I said. So any points represented on this plane is in the polar form. So if I keep r equal to 1 in this equation, if I keep r equal to 1 in the Z transform formula, the Z transform formula becomes Fourier transform. So I will say that my Z transform points, all the points in Z plane, they are not contributing the Fourier transform, but only those points for which r equal to 1, they are contributing the Fourier transform. So what are those points? So those are the points which are lying on this circle perimeter, because this is a distance, radius r equal to 1. That's why it is known as the unit circle. So as I said, it is a polar plane. So the points will be represented like this. So all having the same distance from the origin, and that is equal to 1. they all are contributing the Fourier transform. So I will say all points on the unit circle contribute Fourier transform, and you can say that Z transform becomes Fourier transform on the unit circle, right? So I can also put Z equal to e power j omega to get Fourier transform from Z transform. So let's say you have a signal a power n, right? So you can take Z transform of it, and that is 1 minus a Z inverse, right? And you can substitute Z equal to e power j omega to get the Fourier transform. But this you cannot do for the signals which are increasing with the time or the constant with the time. Okay, because for them Fourier transform does not exist. So if your a power n is like this, and that will happen, let's say a equal to 0.5. So when n is increasing, definitely it will decrease. So in that case, you can substitute z equal to e power j omega to get its Fourier transform. So for 1 upon 1 minus a z inverse, I have substitute z equal to e power j omega. So that is your Fourier transform. Okay, so this you can do, remind this, this you can do only for those signals for which the Fourier transform exists. So this is all about this lecture. I hope that you have learned that how Laplace transform and Z transforms are evolved from the Fourier transform. As we know that the Fourier transform formula fails for the signals which are constant in the magnitude with respect to time, and which are having the magnitude increasing with the time. So that problem is dealt by the Laplace transform and the Z transform. So Laplace transform deals the problem of the continuous time signals, while the Z transform deals the problem of the discrete time signals. So thank you very much for giving your precious time. I hope you have enjoyed this video. So please like this video, and you can share this video to others. So thank you very much once again.